So now let us get into the math mode of looking at things. Okay. Now I am going to formulate a mathematical model. Why? So far I have been comparing two random variables, I do not care about what is input, what is output, right. Now in the jargons I have defined what is called as a response variable, what is called as a factor. So response is my output, factor or treatment is my the way that has given rise to the response, the variable, the input that has given rise to the response, that is what response is basically, right. So now I am going to formulate a model between the treatment or factors and the response, and that model is going to be a linear model to begin with, and now I can complicate, and this also gives you a nice way of including interactions. Okay, we will look at this. So now what am I going to have? I am going to have Yij. What is I, what is j? Any idea? 1 I is the factor. How many factors? Like how many treatments? Basically you also call it as treatment or factors or treatment. How many treatment methods you have used, right. So suppose to measure, to treat a particular disorder, if you have used n drugs, this n are A methods, these A methods are your treatments. Okay. So that is my treatment or factors, and what is j, n? N is the total number of samples. Okay. So Yij is a matrix, for each method you will have data points, n data points, right. So this is Yij, this is the total data. What am I assuming? What is my assumption? What is the model here? What is the model stating? If you look at the model, what is the model? Yij equals to mu plus tau I plus epsilon ij. What is this? What is this assuming? Linear, yes, fine, that is linear model. What is the underlying idea behind formulating this model? I am saying Yij equals to this. What is the idea behind formulating? What is assumptions idea? See, your response, your output response as an average, as a normal average, let us say mu, okay, that is my average, and there is a deviation from the average due to two things. One is noise, which is epsilon ij, that is a noise, and the other deviation in your response could be due to what? Could be due to the treatment. Okay. So your deviation from, so your output, what am I saying? Your output is composed of a standard, a normal mean component plus an additional component that is due to treatment and a component due to noise. I do not need to, I will remove, that is why I am saying I do not need to. I am, what is my idea, what do I want? Which treatment is better? Why do I want to compare about the overall mu? I do not even need that mu, okay. But the idea behind is what? Response in so any variable, response variable will have a normal output, even if you do not treat, there is an outcome, right. That outcome, average outcome, is what I call it as mu. Because of your treatment the mu may change or may not change. I am assuming that changes by a level of tau I, and it is also not changing, it is not also varying. So mu is, so suppose if I want to draw, let us say this is my response variable y, okay, this is, you could have the data points, samples, etc. Okay, let's draw this up to this. Okay. Now there is an average component, this is what I call it as mu. Then there is a deviation from mu, center value, because of what? Treatment and noise. Now the question is what is the treat, if I want to say whether my treatment is working better, what do you say? How do I prove it? Suppose I want to, this is my model, I want to prove that my treatment is working better. How do I prove? What do I want to prove? I mean statistically I want to say that this treatment is not equal to 0, that is my treatment is significantly contributing to the outcome. How do I do that? You understand the model now? Yij equals to mu plus, it is independent, not mu I, not mu j, mu plus tau I plus epsilon ij. What is epsilon ij? Very simple, that is the assumption we would have made. What is it? IID normal 0 sigma squared, right. What is the assumption I would have made? This is exactly the noise. When I said noise, what you should have guessed? Central limit theorem. So noise is typically Gaussian distribution. It is also independent, so that you do not need to model the noise. If it is dependent, then you want to model the noise. You do not want to model the noise. So typically you assume the noise is totally not modelable. So it is independent, and because it is noise, it is going to follow a central limit theorem typically, and then therefore it is Gaussian distribution. And my assumption it has a 0 mean and variance of sigma squared, okay, like what you saw in the earlier normal 0 sigma squared, that is my assumption, okay. So we will see what is the effect of these assumptions, okay. So now, so I could have written the model as mu I plus epsilon ij, where mu I equals to mu plus tau I. Okay, I could have also written like this, okay, I could have written very well mu I plus epsilon ij. Now if I want to say mu I is significant, how do I do this? So let us say second model mu I is significant, how do I prove it? How do I see this? Mu I is significant, mu I has a significant contribution to y, how do I prove it? Ith response, ith due to ith treatment. There is only treatment and data points. I is treatment. Yij, I stands for ith treatment, jth data point. So now I want to say this treatment is better, and this is the model I have assumed. How do I go about doing this? Mu I plus epsilon ij. How do I do? We all learnt about correlations, etc. So how do I do? So there is a variability in y, there is a variability in y, agreed, there is a variability in y, because I showed you the data, right, there is a variability in the y. If your treatment is important, if your treatment is doing its job, the variability should have come from what? The variability in your output yi, yij should have come from what? Should have been due to treatment, and that variability in treatment should be definitely greater than variability in noise. You understand? So what are we saying? The variability in your output due to your treatment should be significantly greater than the variability due to in output due to noise. You understand what are we talking? So your output has a variability. Now we are not even talking about mu. We said there is an overall mu and we take it as mu plus tau I. So we can club it, we call it as mu I. Okay. So your original model mu Yij, what have we assumed is mu plus tau I plus epsilon ij. So now your output is composed of three components, a basic average component plus a tau I component plus an epsilon ij component. Now your output is affected due to your treatment as well as your noise, that is very important, your treatment as well as your noise. So far you have never considered noise at all, you have only considered one random variable separately or two random variables and then compared, but in reality your output is composed of noise as well, right. Now in order to say that mu I is significant, what does it mean? Your variability in y should have been predominantly due to your what? You are doing treatment, you are doing multiple treatments, right, you are doing collecting data from different treatments. So there will be variability in y, but the variability in y should be due to what? Should be because of the method you treated or the method you approach. It should not be due to, the significant portion should come from treatment compared to noise. So in other words, if I say, if I take a ratio of Now I am going to do simple F test, right. So I am going to check for ratio of the contribution due to treatment and the ratio of contribution due to the ratio of contribution due to treatment and noise. If this is significantly greater than 1, then what do I know? For all degrees of freedom blah blah blah, I know that treatment is effective. I do not know which treatment is effective, at least one treatment is effective. That is why the variability in Y is predominantly due to treatment. If this is close to 1, that means all your treatments are useless, basically it is equal to noise. You will always have variability in Y, right. You understand, you will always have variability in Y because there is always noise component. But the question to ask is this variability in Y can be attributed to treatment or should it be attributed to noise? That is the question you want to ask, right, and that is why two variances comes into picture. You understand, this is how we approach the comparison of mean itself using variance. Make sense?
So with respect to the graph, can we see?
We will come back, I will show you a better detailed one, okay. So let us understand this, okay. So I have 4 treatments, in this case I have 4 treatments, okay, and each of this is what? Mu I equals to mu plus tau I, okay. Now this is my first distribution, second, third, fourth, and what am I assuming? All of them are having same variance. The difference is only in the mean, that is due to treatment. Now my question is, are these all the means same or different? The variances are assumed to be equal, okay, that is an important catch, okay. The variances are assumed to be equal, and that is why I said your output is also normally distributed, because you are also assuming the noise to be also normally distributed, your output is also normally distributed. So in other words, your Y is typically is this, follows this mu plus tau I, follows this. Yes, all of, see the mean shifts, I want to capture that, I will come to that, I will want to capture that using the variance changes, okay. So let me come back to that, okay. You will see once I start analyzing this this thing. So we have Yij equals to mu I plus epsilon ij, we have mu I equals to mu plus tau I, mu is the mean of the ith treatment, okay, and each treatment defines a population that has a mean mu I. So each treatment itself is a population. Remember, we have population for treatment 1, population for treatment 2, population for treatment 3 and population for treatment n, and all of them influences your, each one of them influences your output, and we want to know whether at least one of them significantly influences your output Y. Make sense everybody? Clear? So if you go back to this, this is what? Treatment 1, treatment 2, treatment 3, like your biomedical case or whatever you want to relate it to. So these are my mu plus tau 1, tau 2, tau 3, and what am I assuming? The normal distribution I will come to, if you look at it, I am assuming this population is what? Normally distributed with same variance. I am not assuming the output is normally distributed with same variance, okay. I am assuming your inputs itself is, it's each one of them is a population, you all understand, each one of the treatment itself is coming from a population. So each treatment itself is normally distributed, okay, with an underlying population as mu plus tau I, mean as mu plus tau I and variance as sigma squared. Not SS is sum square divided by n minus 1 is variance.
The values are different because number of observations.
Yeah, obviously, it is only a data thing, right. It is,
We assume them to be equal.
in data you will never get them to be equal, it is only an assumption, right. So, because of the limited number of samples you will not get them anyway to be equal. Okay. So, I am having this 3 populations, 3 different populations, assumption is 3 different means are different, okay, and my null hypothesis is all of them are equal, my alternate hypothesis is at least one is different, okay, and each of them follow a normal distribution with same, you know, means, each of them follow a normal distribution with mean mu plus tau I and variance sigma square, same variance sigma square. This is the setting. Clear? So far so good, okay. And this is the model which we have talked about, the relation between the output, okay. So, you have your output, so this is a simple example, okay. Let me take you this example so you will know. So, this is, okay, a hardwood concentration, okay. So, we have a range of hardwood concentration, okay, and a manufacturer makes grocery bags, interested in grocery bags, and product engineering thinks that the tensile strength is a function of hardwood concentration. So, tensile strength and hardwood concentration are related, that is what they think. So, we will have this kind of problems everywhere in biomedical, all of the domains, I take across domains. So, this is my tensile strength in, these are my tensile strengths, okay. How many factors are here? How many treatments are there? How many treatments are there? 6 or 4 or what is it? How many treatments are there? How many treatments are there? Look at this table, can you tell me how many treatments are there? What is a treatment? How many treatments are there? What is the treatment variable? Hardwood concentration is my treatment, because that is my input that I can change. So, how many levels of treatment? 4 levels. So, these are 4 levels. Where is the 6 coming from? Where is the 6 coming from? So, I have taken 6 specimens, 6 specimens, okay, okay. So, they have decided to make up 6 test specimens at each concentration level, okay. Specimen 1 at different concentration level, specimen 2 at different concentration level, etc. Okay. So, there are altogether there are 24 observations, right. Now, what is Ij? I is my treatment, J is the number of data points at that, you know, at that for that level, that is J equals to, goes from 1 to 6, I goes from 1 to 4, clear. J goes from 1 to 6, I goes from 1 to 4, and it is a matrix now, okay. So far so good. Now, what does this actually, what does this graph mean? I am saying this hardwood concentration itself at 5% follows what? This data point follows what? First row follows normal distribution with mean as mu plus tau I and variance as sigma square. The second also follows the same idea, but with mean mu is tau 2 and sigma square, same thing. Understood? Everybody? Clear? This is the assumption. Why do I need to make equal assumption variance? Why do I need to make equal variance assumption? These are the questions at undergraduate level you will never learn. At least at this level you should ask these questions. Why do I need to make this assumption of equal variance? Any idea? There goes the answer. Homogeneity, right? We are, so paired t-test, remember paired t-test, what did we do? we maintain homogeneity. If you do not maintain homogeneity, your results are going to be erroneous. That is why first question is random sampling and then try to maintain homogeneity. Okay. We are maintaining homogeneity here. Okay. Otherwise, the variations could be due to what in the output, could be not only due to treatment, but the underlying variation of due to, suppose there is a sensor reading which gives you temperature currently in this room. Let us say I measure in this room one sensor, okay, it gives me 25 as the mean temperature, but its variance is 2, let us assume variance is 2 degree, which is huge for a temperature sensor, but let us assume. Okay. Now there is a relatively better temperature control room, let us say in my lab, or my lab is not that controlled, so we will go to some other place where temperature is better controlled. The sensor gives me 22 as the reading, but it gives me plus or minus 6 as the standard deviation or variance, variance is 6. In this sensor reading variance is 2, that sensor reading what is it, variance is 6, but that mean is 22, this reading is 25. Now can I compare these two and say that really the temperature is 22? If it is equal variance, then I can say something. If I have used the same sensor here and there, then I can compare and say, hey, this room is worse temperature compared or slightly higher in temperature compared to the other room. Why? It has the same variability, both the sensors, so there is no change in due to sensors, it is only the underlying system that has caused a variation. Now if I start changing sensors and the variance is very different, then I have to account for it separately, okay, which is not what ANOVA does. ANOVA is a simple one, so ANOVA assumes the variance of the underlying population is similar, normal, but that does not mean that we do not know how to handle if you use two different sensors, but that method is not a part of ANOVA. So you have to assume the assumptions you have to be very clear with the assumptions, okay, before we proceed. When can ANOVA be used? Okay, people blindly use ANOVA, that is of no help. You have to see that the underlying samples are normally distributed with equal variance. So the treatment one, the variability due to treatment. So in terms of biomedical, what am I saying? If you give a drug, multiple drugs to a group of to treat patients of certain category, you have to be very clear it is not biased, meaning you do not give a set of drugs to one set of drugs to female, one set of drugs to male and then say look the underlying variability is the same, there is treatment, the change is due to treatments. What do? You completely randomize and then say this pool has kid as well as an adult as well as a male, a female, aged person, etc. Similarly the other group also has all of these combinations, so that the variability that is arising due to sample is equal in both. That is why we call it as what we call it as random trials. That is the first assumption we made in ANOVA. Now you understand why this assumption is very important. The data are randomly sampled. If you do not do that, the variances will not be equal. Clear? And now the variances of samples are equally assumed. This is what for each treatment. So this row has this, okay, clear, make sense. Now what are we comparing? We are comparing the mu's, okay. Now if I want to compare, what do I say? Look, all the variability is the same, all the variability along each row is same, for all the treatments it is the same. Now I have to compare this variability against what? Variability due to noise. You understand? Variability due to treatment has to be compared against variability due to noise. You understand? Then I can say look, the variability due to noise is very less, my output is varying mainly because of my treatment and not because of my noise. So at 5% and 7%, the change is due to the change in variability or the change in the shift is due to treatment and not due to noise. That is what we want to prove. Does it make sense? Is the framework clear? Okay. So now a bit of math. Okay. So there are two kinds of models. There are two kinds of models. ANOVA, the same model is actually can be used at two locations. One we call it as fixed effects model, the other one we call it as variance model, variability model, okay, random effects or variance model. So there are two kinds of models which is called fixed effects and random effects. Any idea what is this? It is the same model. In one case we call it as fixed effects and in the other case we call it as random effects. Now if you go back in general, if you go back to this example, let us say the question is, am I interested only in 5, 10, 15 and 20 percentage, or am I interested in, or is this a subset of a bigger population? You understand, we know that treatment, each row itself is normally distributed, because at this treatment the samples you collect is from a normally distributed population. Now I am asking, is this treatment itself fixed or the treatment is a part of a bigger group? You understand my question or no? So if you take treating a disease, underlying disease, so you come up with let us say 4 drugs, one is based on let us say simple paracetamol based, one is based on paracetamol and ibuprofen, and one is based on cytizine based, etc., right. All of them are 4 different drugs. Are you interested just in these 4 drugs, or is this 4 drugs is a sample of subset of a bigger population? This 4 drugs itself could be a subset of a bigger population. Remember, crocin is what? Is a drug, is a brand name. What is the content? How many companies manufacture it? Many. So now am I testing for the effectiveness of crocin or am I testing for the effectiveness of calpol? That is a question to ask. You understand? So if I say ibuprofen or if I say antihistaminic, which is what your cytizine is, right, simple way, day to day I am talking about antihistaminic. Are we interested in antihistaminic effectiveness, or are we interested in cytizine with this content and with this level as a drug? What are we testing for? So is the treatment themselves fixed or is the treatment itself is random, meaning is the treatment a subset of a bigger population? That is a question to ask, and that will give rise to different kinds of analysis. The outputs is still the same model, but the analysis will be different. In the first case, when your treatment is fixed, then I can ask this question. What is the question? I can say whether all treatment means are equal to 0, because I am interested in this particular fixed treatments. But when the treatment itself is a subset of a larger population, I am not worried about the drug crocin, I am worried about calpol as a drug that will solve this problem. I am interested in antihistaminic, not in cytizine at this level. You understand? So when I ask that kind of question, you will not have this null hypothesis. This null hypothesis is for fixed effects model. What do I mean by fixed? You are only interested in this particular levels, particular treatments. Your treatment is fixed. It is not a subset of larger population. So if I say 4 treatments, yes, you are only interested in these 4 treatments. I only care about these 4 branded drugs, that is it. I am not cared about others. Then you are saying treatment is fixed. So that is called fixed effects model, and your null hypothesis is that all the treatments are same. Your alternate hypothesis is at least one treatment is different. Whereas if my treatment itself is a subset of a larger population, then it becomes what is called as random effects model, because your treatment is itself is a subset of a bigger. So remember how many things now we are laying up. Each treatment itself is outcomes are a random, and that comes from a normal distribution, and each of the treatments or all treatments are following a normal distribution with variance sigma square, okay, and mean is just changing. and now this treatments itself is a subset of bigger population. That is where random effects model is. If these treatments are fixed, then we call it as a fixed effects model. So there are two kinds of hypothesis, one for fixed effects, the other one is for random effects model. So in here we will develop the hypothesis or analysis of variance for the fixed effects model. Random effects model, yeah.
Random effects model, we will also consider the same variation within the population of the treatment.
We have to consider the variance in the population of the treatment. Perfect, perfect. Yes, we will not worry about mean at all, because when we worry about mean, you are only worried about these 4 outcomes, 4 treatments. I will talk about the variability at the population level. Good. So that will be my null hypothesis. We will come back to that. That is a good catch. Okay. Clear? Make sense? Fixed effects and variance model. Am I making sense or not? Okay. Now I am assuming in the fixed effects model the summation of tau I equals to 0. Summation of not tau I, not individual tau I, the summation of tau I should be equal to 0. Why is it? This is valid. Why is it? This is my model, mu plus tau I plus epsilon ij. I am saying summation of tau I should be equal to 0. And remember, epsilon ij equals to normal 0 comma sigma squared. Okay. So now why summation of tau I should be equal to 0? Look, something should be above the mean, something should be below the mean. When you add only you get mean. So some treatment should have contributed to positive variation, some treatment should have contributed to negative variation, and noise has contributed nothing to the variation, nothing to the mean. So noise mean is already 0. So Yij equals to mu plus tau I, the mean of the noise is 0. So now if you compare, if you sum it up, then it should be equal to 0, because the average value of Yij is what? Mu. So the average value of tau I should be 0. That is summation of tau I should be equal to 0, because the way we define the model, it is because the way we define the model, summation of tau I should be equal to 0, not individual tau I. The summation of tau I should be equal to 0, because the way we define the model, Yij is a deviation of Yij is due to a central effect which is mu, the overall mu plus a tau I plus the noise. The noise we have assumed that it has no mean value, that is 0. So then the above and below, the mean is due to treatment effects, and on an average they should be equal to 0, so that you get the center. So that is why summation of tau I equals to 0. Okay. This your books won't cover, so please pay attention. I am going into as much tiniest details as possible, so that you are very clear. Okay. So summation of tau I should be equal to 0, and now I am going to define some mathematical quantities which will be used in our ANOVA calculations, etc. So we have Yi dot, the dot stands for summation along that particular axis. So Yi dot is what? Summation along j axis. Y dot j is summation along I axis, and Yi dot bar is nothing but Yi dot divided by n. Okay. And Y dot dot is what? Is the grand sum, that is summation along both the axis, and Y bar dot dot is the grand average. The dot stands for summing along a particular axis. So if I put Yi dot, I am summing it along j axis, and if I put a bar, you all know it is the average value. So Yi dot bar is nothing but Yi dot divided by how many j values are there? N j values. So you have Yi dot divided by n, and Y dot dot is nothing but summation along both the axis, that is it is the summation of the matrix, and the average value is given by Y bar dot dot. Clear? And this is my, and capital N is the total number of observations, that is A times N, where A is the number of treatments and capital small n is the number of observations for each treatment. So capital N is nothing but A times small n, which is the total number of observations. Make sense? Okay. And now I have my null and hypothesis clearly defined. tau naught, this is for fixed effects model only, we are all talking about fixed effects model, okay, and this is summation tau I equals to 0 and this is my null and alternate hypothesis, okay. Now we are going to have some derivations, do we take it today or do we take in the next class? The framework is set, so the next class I will finish up the theory and move on, okay.